When you think about decarbonizing the global transport sector, your mind probably goes straight to electric vehicles. Massive battery packs, maybe fuel cells humming quietly in a city bus.
That's the popular narrative for sure.
But what happens to the internal combustion engine? The device that has, powered civilization for over a century. Does it just disappear?
It's a great question.
Today, we are tackling a critical, often overlooked part of that future. The necessary, dramatic, and arguably revolutionary evolution of the traditional engine itself. We're not talking about EVs. We are deep diving into the strategic future of the zero-carbon engine, or ZCE. So why are these engines still fundamentally relevant, even crucial, in a future we're all defining by the goal of zero emissions?
That is the pivotal question, really, and it requires a high-level, detailed analysis, which is exactly what our source material gives us today. We're analyzing what is essentially a top-tier strategic consultancy report, a technology blueprint known internally as RoadMap 3.0.
So this isn't just a white paper.
Oh, not at all. This isn't just a collection of engineering notes. It's a national-level strategic plan. It's focused intensely on the pathway for zero-carbon engine technology. Our mission today is to analyze the strategy, the current global competitive status, and the granular technical milestones, the specific engineering benchmarks that are set for 2030, 2035, and the ultimate strategic target of 2040.
Okay, so we're treating this like an industrial engineering and strategic business challenge. And what immediately stands out to me is that the strategic significance of this ZCE push is framed across three absolutely crucial national dimensions. It goes far beyond just cleaning up tailpipe emissions.
And no matter, this is viewed as a foundational strategy for future industrial competitiveness and, frankly, national stability. The first dimension is energy security.
Right.
By proactively developing engines that can use domestically produced green fuels, specifically green hydrogen, H2, and green ammonia, NH3, the goal is to systematically and structurally reduce reliance on imported fossil fuels.
Which is a huge vulnerability for many economies.
A massive one. This shifts energy autonomy inward, providing a huge strategic hedge against the volatility and, the political risks tied to international energy markets. It's really about securing the nation's energy future through diversified domestic capability.
That makes the ZCE push sound almost like a macroeconomic policy tool, not just an environmental one.
That's a perfect way to put it. And that leads right into the second dimension, which seems to focus internally on protecting the vast industrial base that's been built up over decades.
The industry upgrade component.
Precisely. We can't overlook the sheer scale of the established traditional engine supply chain, the manufacturing capacity, the skilled workforce, the thousands and thousands of suppliers. Zero-carbon engines mandate that this entire existing industrial base, from R&D to tooling and mass production, moves rapidly toward high-value, green, and intelligent manufacturing processes.
So it's not about abandoning that infrastructure, but transforming it.
Exactly. It's a necessary, you could say a forced transformation to maintain global competitiveness and ensure that this huge industrial foundation doesn't become obsolete in a carbon-constrained future.
This keeps the existing engineering ecosystem vibrant by giving it a complex, high-stakes new challenge. And then there's the final driver, the one that puts all these technical goals into their necessary context, the dual carbon goals.
Yes, and this is so important for you, the listener, to grasp. Despite the rapid growth of batteries and fuel cells, the internal combustion engine configuration is still forecast to be widely used in the medium to long term.
Especially in certain applications.
Especially in specific hard-to-decarbonize, high-duty and long-range scenarios. Think heavy-duty trucking, think mining equipment, or specialized off-road vehicles. For these applications, ZCEs are defined as a foundational pathway for the transportation sector to achieve the national 2030 carbon peak and the subsequent 2050 carbon neutrality goals.
So if you don't decarbonize the engine, you simply cannot hit the targets for those critical sectors.
You just can't. It's mathematically impossible.
That reframes the entire discussion. ZCEs aren't a niche. They're a critical bridge solution for the heaviest lifting. Now let's define the research scope here. Our sources make it clear that this strategic push is hyper-focused on two primary future fuels.
Correct. The zero-carbon engine research is concentrated entirely on hydrogen H2 engines and ammonia NH3 engines, and the roadmap differentiates their application, which is important.
How so?
Passenger vehicles, or PC, will primarily focus on green hydrogen integration, leveraging its speed and efficiency benefits. Commercial vehicles, CVs, will develop systems for both green hydrogen and green ammonia, which exploits ammonia's raw material availability.
And the architecture supporting this isn't just a minor tweak to an existing diesel engine, is it? It's a complete, complex technological framework.
It is. It's defined as the zero-carbon engine plus zero-carbon fuel. And crucially, this system is not successful unless it is supported by 4 integrated technological pillars that have to advance at the same time.
Okay, what are they?
First, high-efficiency combustion optimization, getting the most energy out of these new, tricky fuels. Second, key component application designing the injectors, the materials, the turbochargers that can handle them. Third, high-efficiency after treatment, cleaning up the resulting emissions, especially from nitrogen. And fourth, intelligent control systems using smart algorithms to manage these complex new fuels.
So it really requires breakthroughs across the board.
It does. It's a total system overhaul.
Okay, let's unpack this. Before we gaze into the 2040 crystal ball, we need a clear, objective benchmark. Where does this technology stand today compared to the global leaders? Are we playing catch-up or are we driving the innovation?
In the hydrogen engine space, the assessment is nuanced. The report positions the domestic effort as a fast follower, but one with tremendous potential. Foreign companies, well, they certainly have the advantage of time. They've accumulated significant technological experience and achieved earlier market maturity.
So who set that early bar for H2 engine development, particularly in the heavy-duty sector?
The leading forces are mainly Germany, the US, and Japan. Looking at commercial vehicles, Germany's DEUTZ, in partnership with a company called KYU, is a key benchmark. They developed a 7.8-liter H2 engine using intake port injection, and their reports indicate they are already nearing mass production readiness.
Nearing mass production, that's a huge step. And in the U.S.?
The U.S. giant Cummins is also highly active. They have their 6.7-liter direct injection H2 engine, which is already being deployed globally in pilot programs, for instance, in Tata trucks in India. They're clearly focused on getting high-power, reliable engines into the field right now.
And on the passenger vehicle side, is hydrogen engine research competing directly with fuel cells?
Absolutely, and it's fascinating. The Japanese auto sector, particularly Toyota, is notably researching H2 fuel cells and H2 engines simultaneously. This indicates they see a dual kind of complementary role for hydrogen power in passenger transport.
So it's not an either situation for that?
Not at all. And domestically, our own manufacturers like GAC, Geely, and FAW have rapidly responded. They're moving quickly into initial demonstration runs for hydrogen-powered passenger vehicles. So while the fundamental R&D may have started abroad, the domestic catch-up effort is swift and clearly prioritized by those overarching dual carbon goals.
And that domestic catch-up isn't just theoretical. We've seen major domestic players like Weichai, Yuchai, and FAW Jifang committing heavily to developing these large 13 to 16-liter heavy-duty engines. They're aiming for small batch production around 2026.
That's right.
That puts them on a collision course with international competitors very, very quickly.
It does. And this leads us to the crucial technical benchmark analysis provided in the sources, a moment where the data reveals a startling paradox in that fast follower designation.
Okay, let's focus on that specific performance data. The comparison table of heavy-duty hydrogen engines. What do the raw numbers reveal about domestic capability versus global maturity?
The key insight for you, the listener, comes from comparing international models like the Cummins X15H and the domestic Yuchai K16H. And we look at one metric above all others, maximum effective thermal efficiency, or TE.
And what are the global benchmarks for that? Where does Cummins sit?
The Cummins X15H sits at 45% TE. European leaders like Scania, Daimler, and DEUTZ are typically in the 42% to 44.5% band. Pretty impressive numbers for a new fuel.
Okay.
Exactly. But the domestic Yuchai K16H, despite still being in the performance development stage and not ready for mass production, it already reports a globally leading maximum effective thermal efficiency of 51.5%.
Wait, say that again? 51.5%?
51.5%.
That is a truly shocking number. I mean, 50% thermal efficiency has long been the holy grail for internal combustion engines, even for advanced diesel. And here we see a domestic hydrogen engine prototype exceeding that in the lab.
This is more than just a number. It demonstrates a major world-class technological breakthrough in combustion science and fuel utilization efficiency. It indicates that domestically, we have the theoretical and scientific capability to outcompete global rivals on fuel economy. The efficiency breakthrough is, in principle, secured.
So that leads directly to the core strategic paradox then. If the domestic technology can achieve superior single-point performance, a 51.5% peak, why are we still classified as fast followers and deemed to lag overall?
Because efficiency is merely the starting line, the report makes it very clear. The competitive lag is not in scientific genius, but in industrial maturity and systemic integration.
Okay, break that down.
While Utah is demonstrating this leading performance in a lab, DEUTZ and Cummins are nearing or already achieving mass production with tested, durable supply chains. The domestic firms lag in two critical areas: systemic integration, which is how well all the high-efficiency engine components work together reliably over millions of cycles, and supply chain scaling.
So the challenge isn't the research, it's the transition from a single high-performance lab engine to 100,000 mass-produced engines that operate reliably for 1,000,000 kilometers.
Precisely. The gap lies in the engineering verification. The cost reduction through volume, long-term durability metrics, what we call the B10 life, and establishing a refined supply chain that can consistently deliver the required quality and tolerance for high-pressure hydrogen components. The 51.5% is a victory in science. The fast follower status is a challenge in industrial engineering and scaling.
That clarifies the position perfectly, leading scientifically but trailing in industrial readiness. Now let's pivot to the second major fuel category in this roadmap: ammonia or NH3 engines. This presents an entirely different set of opportunities and technical hurdles.
It does, and this is where the domestic strategy leverages a massive, unique structural advantage in raw materials supply. China is the world's largest liquid ammonia producer.
That's a key piece of strategic data.
It is. This provides an abundant and, crucially, a cost-controlled raw material supply base. When you factor in the high cost and global competition for green hydrogen supply, the commercialization pathway for green ammonia is theoretically much more feasible from a logistics and economic standpoint. It's a huge strategic asset.
And the Research Foundation is already leveraging this advantage.
Absolutely. We see significant academic and industry breakthroughs, particularly from institutions like Tsinghua University, Tianjin University, and Shanghai Jiaotong. A major foundational milestone happened back in 2022.
What was that?
The successful ignition of the first domestic ammonia diesel heavy-duty engine. It was a collaborative effort between Dongfeng CV and Tsinghua. This proves the core feasibility for large commercial applications.
So the foundation is solid, but we need to address the elephant in the room. Ammonia is notoriously challenging to burn effectively in a vehicle engine. What are the key hurdles preventing NH3 from becoming a widespread zero-carbon fuel today?
The technical baggage is substantial, and the report outlines three major roadblocks. First, combustion stability. Ammonia has a very low laminar flame speed,
Meaning what, exactly?
meaning it burns excruciatingly slowly compared to diesel or gasoline. This currently restricts its practical use to stable, low-speed applications like marine engines or stationary power generation. For dynamic, high-speed vehicle use, this slow burn means the engine struggles to respond and maintain efficiency.
So how do you counter that instability?
To compensate, ammonia requires very high ignition energy. This necessitates the use of pilot fuels, typically a small amount of diesel or biodiesel acting as a sort of spark plug accelerator, or assistance from onboard generated hydrogen, what's called H2 assist, to ensure a stable, rapid burn.
So you need a second fuel. That adds immediate mechanical complexity.
It does, and then there's the second hurdle, the safety and environmental aspect.
Right.
The second, and arguably most complex challenge, involves safety and emissions. Ammonia itself is toxic and corrosive, which demands specialized, highly durable materials for every single component that touches the fuel, from the tanks to the piping and injection systems. This adds significant material science complexity.
But the biggest issue is what comes out the tailpipe.
Exactly. The biggest emission challenge is controlling the nitrogen compounds. When ammonia burns, it produces high levels of nitrogen oxides, or NO-plukes, and critically significant volumes of uncombusted ammonia slipping out the tailpipe, what we call NH3 slip.
So the after-treatment system has to deal with both the NOx created by high-temperature combustion and the unused ammonia, which is also toxic. That sounds like a technical nightmare.
It is a massive, bespoke technical hurdle. And this explains why, globally, ammonia applications are strictly limited to marine and power generation sectors. They are not yet deployed in passenger or road commercial vehicles because those dynamic combustion and complex emission hurdles have simply not been overcome for varied road use.
So the domestic CV-NH3 roadmap is therefore much more exploratory than the H2 roadmap.
Much more. It's focused intensely on proving eventual vehicle feasibility.
What's fascinating here is that achieving this level of systemic transformation isn't just about making a better piston. It's about establishing a new market structure supported by systemic collaboration. This report lays out 5 core strategic pillars that define the ecosystem needed for success.
That's the classic management consultant approach, right? Recognizing that technology has to be integrated into a supportive policy and industrial framework. The core vision articulated is that by 2040, ZCEs will be the core force driving the transport transition, forming a complementary market structure alongside pure EVs and fuel cell electric vehicles, or FCEVs.
And where exactly does the ZCE fit into that complementary structure? Where is it designed to thrive?
It is specifically designed to dominate the high-load and long-range scenarios. Think of vehicles that carry a high payload for thousands of kilometers, or vehicles that require sustained high-power output heavy commercial vehicles, long-haul freight, and potentially high-efficiency compact passenger vehicles used in hybrid powertrains.
So they're exploiting the high energy density of H2 or NH3.
Exactly. And utilizing the infrastructure and expertise of the existing ICE supply chain, where batteries and fuel cells struggle with weight and charging time.
This vision is backed by a very detailed 3-phase strategy leading up to 2040. Let's break down these distinct stages of growth and maturity.
Okay, Phase I, the foundation and demonstration phase, runs until 2030. The immediate goal here is productization and achieving the critical breakthroughs in core combustion technology that bridge that efficiency gap we talked about earlier.
So this is about proving the concept.
It is. This phase focuses heavily on demonstration runs in controlled environments, like specific urban logistics fleets or fixed-route city buses, and achieving self-sufficiency in key components. The report explicitly mandates that by 2030, the maximum thermal efficiency for a commercial vehicle hydrogen engine must reach 47%, and a passenger car hydrogen engine must hit 45%. It's about proving the potential in the field.
So 2030 is about proving it works efficiently and reliably in limited controlled market environments.
Yeah.
What's the fundamental shift in the next 5 years into Phase 2?
Phase 2, the maturity and penetration phase, runs until 2035. This is the critical transition from laboratory success to industrial scale. The technology must be fully mature, costs have to be aggressively reduced through volume, and mass production needs to start in earnest.
And there are concrete market goals for this phase.
Yes, very concrete and aggressive market penetration goals. ZCE-equipped vehicles need to achieve 5% penetration in the advanced hybrid passenger car market and 8% penetration in the traditional energy medium and heavy commercial vehicle market. This phase is purely about market competitiveness and scaling up.
That 8% penetration in heavy commercial vehicles by 2035 is an astonishingly ambitious goal, especially considering the exploratory nature of ammonia technology you just described.
It is. It implies immense confidence in the speed of engineering development. It suggests the RoadMap designers believe that the supply chain advantage in ammonia will rapidly compensate for the technical hurdles.
Okay, and the final goal, Phase 3, leadership and integration, runs until 2040.
This is the moment for establishing global market dominance and realizing autonomous control over all key components, eliminating reliance on foreign technology. The market goals increase significantly: 8% penetration in advanced hybrid PCs and a formidable 15% penetration in the heavy-medium CV market.
You have 2%.
By this stage, ZCEs are mandated to be leaders in critical, high-value transport sectors.
Moving from the timeline to the structure, let's look at the systemic pillars that underpin this success. The report is clear this isn't just a technical exercise. It requires a whole-of-society approach.
Right. Pillar number 1 is deep integration of government, industry, and academia, what they call synergistic innovation. The sources stress that policy must actively guide and incentivize innovation, supporting the transfer of technology from university labs to large-scale industrial application.
And standardization.
And, crucially, establishing the necessary safety, testing, and regulatory standards. It's about building a robust green vehicle ecosystem where regulatory risk doesn't stifle progress.
That's a mandate for policymakers to keep pace with the hyperspeed of engineering innovation, which is often easier said than done.
It really is. Pillar 2 is synergy with new energy vehicles, NEVs. This is a crucial clarification. ZCEs are explicitly designed to fill the functional gaps left by pure electric or fuel cell solutions, especially where high load and high duration are mandatory, while leveraging the inherent advantages of the existing ICE supply chain and engineering expertise.
So they are complements, not competitors.
Exactly, they're not competitors in the overall decarbonization strategy.
And Pillar 3 brings in hybridization, recognizing that in the immediate future, ZCEs won't be standalone power plants for every application.
Correct. Synergy with hybrid systems. ZCEs are considered critical enablers for advanced hybrid powertrains. By coupling these zero-carbon engines, particularly the high-efficiency H2-based units, with electric motors, the overall energy utilization efficiency and the emission reduction effect are boosted significantly.
So it offers a cost-effective, high-performance, low-carbon solution.
For consumers who still require the range and refueling speed of an engine system, yes.
And finally, Pillar 4 points toward the inescapable future of all advanced technology.
Moving toward high efficiency and intelligence. This pillar dictates that future ZCEs must deeply integrate intelligent control and electrification technologies. We're moving into the realm of smart energy management, where precise combustion optimization algorithms adjust in real time based on driving conditions, and highly effective after-treatment systems are managed autonomously.
So you're turning the traditional engine into a complex, intelligent power unit.
That's the only way to achieve the near-zero emission goals.
Okay, here's where it gets really interesting, the part we need to dedicate significant time to. The specific technology roadmaps. This plan is custom-tailored for passenger cars versus commercial vehicles, and then split again by fuel type. Let's start with the hydrogen roadmap for passenger vehicles PCH2.
The overall mission for PCH2 is a relentless pursuit of extreme thermal efficiency and near-zero emissions, with the primary application being in those advanced mixed-fuel hybrid configurations. And the barriers here are unique to the passenger car segment.
What are those specific PC technical and market barriers that have to be prioritized and overcome first?
On the technical side, the primary obstacle is just the volatile nature of hydrogen itself. We need immature H2 storage and supply systems to mature very rapidly. Hydrogen's extremely wide ignition range makes R&D difficult, increasing the risk of what's called premature ignition, or knock, under high-load conditions.
How that can destroy an engine, right?
It can destroy an engine very quickly. Furthermore, the durability of high-pressure hydrogen injectors, which have to operate millions of times in a short-cycle urban environment, is a key engineering issue.
And the market and policy barriers.
Market-wise, the cost of green hydrogen remains high, and the refueling infrastructure is sparse. It's that classic chicken and egg supply-demand mismatch. Policy-wise, the report stresses the distinct lack of specific demonstration, testing standards, and clear regulatory frameworks for PCH2 vehicles, making necessary real-world road testing very difficult to execute at scale.
Okay, let's look at the highly ambitious technical targets set for 2030, which kick off this roadmap.
By 2030, the headline goal is a maximum thermal efficiency, or max-TE, of 45%. And crucially, the target isn't just a peak number in a lab. It's about usable, real-world performance.
What do you mean by that?
The high-efficiency zone, where the thermal efficiency is over 40%, must constitute at least 45% of the engine's total operating map. This ensures the engine is efficient across both urban driving and highway cruising alike.
And the required fuel economy benchmark.
For a typical C-Class vehicle running under the China Light Duty Vehicle Test Cycle, or CLTC, the consumption rate must be reduced to 1.35 kilograms of hydrogen per 100 kilometers. This demands absolute precision in combustion control to meet both emissions and efficiency goals simultaneously.
To achieve that 4 or 5% efficiency and suppress knock, what specific technologies have to be fully mastered by 2030?
The focus is on fundamental combustion breakthroughs. Mastering high compression ratios suitable for hydrogen, developing robust and reliable hydrogen gas direct injection, GDI technology, and deploying sophisticated techniques to actively suppress that early ignition and knock. Simultaneously, the industry has to scale up the application and management of 35 MPa high-pressure gaseous hydrogen storage.
And that 35 MPa capability is the industry standard for daily driving range.
It's the baseline. It's what you need to achieve viable range in a passenger car.
So that's phase 1, establishing efficiency and managing combustion stability. Moving to 2035, phase 2, we see the efficiency goal jump again, and the demand for a wider operating window.
It does. The 2035 goal is a max TE of 47%, and they demand an even larger operational window for high efficiency. The zone over 42% efficiency must now cover 50% of the engine's operating range. This is the phase that transitions the technology to commercialization, aiming for that 5% market penetration in advanced hybrids.
How do they squeeze out that extra 2 points of efficiency and expand the functional range? What's the key technology?
It comes down to mastering ultra-lean burn, ULB, optimization control. ULB means running the engine on a much higher air-to-fuel ratio than stoichiometry allows. This significantly reduces combustion temperature, which in turn reduces heat loss, improving efficiency,
Yeah.
and helps control those tricky NOx emissions.
So that requires even more precise control.
Extremely precise, high-reliability H2 injection systems, and the introduction of advanced, highly efficient catalytic after-treatment systems necessary to ensure near-zero overall emissions. And on the storage front, they need a major breakthrough in 70 MPa high-pressure gaseous storage, effectively doubling the energy density stored on the vehicle.
Doubling the storage pressure is a massive material science and safety challenge in just 5 years, and the final ambitious leap to the 2040 vision for passenger vehicles.
The pinnacle, max TE of 50%, maintaining the high efficiency zone, now over 45% at 50% of the operating map. The ultimate goal is near zero emissions and reaching that 8% market penetration target in advanced hybrids, establishing these ZCEs as commonplace high-efficiency power units.
50% thermal efficiency in a passenger car hydrogen engine. That's not just world-class, it's almost miraculous. What specific technology delivers that final 3-point jump?
The strategy pivots intensely toward intelligence and dynamic control. They plan to utilize dynamic combustion models, AI-driven simulations running in real-time and highly intelligent algorithms for precise millisecond-by-millisecond control over fuel injection timing, pressure, and ignition parameters.
So the engine is basically thinking for itself.
This is where the integration of electrical and intelligence systems truly pays off. And critically, for long-range premium applications, the storage goal shifts to mastering liquid hydrogen LH2 storage technology. This offers the highest possible energy density, but requires managing extremely low temperatures, which presents its own significant engineering challenges.
Let's transition now to the high-demand, high-durability segment. Commercial vehicle hydrogen engines, or CVH2. The focus shifts dramatically from hybrid efficiency to high-load sustained efficiency and, critically, durability.
Yes. The mission here is maximizing power output and ensuring extreme reliability. This is essential for heavy trucks and long-haul transport, where any engine failure translates directly to massive financial losses. The key challenges in CVs are different.
Such as?
A low power density, or kW per liter, compared to current diesel engines, the durability of mid to high pressure injectors under constant heavy cycling, and maintaining stable combustion in high load, high torque scenarios without that destructive knock.
The CVH2 roadmap introduces B10 life as a critical metric. Can you explain that for our listeners?
Of course. B10 life is the operating life, in kilometers, before 10% of the produced engines are expected to fail. This is the true measure of heavy-duty endurance.
Okay, so what are the 2030 targets for CVH2?
By 2030, the target is a max TE of 47%, with a high efficiency zone over 42% at 45% of the map. But the durability target is a B10 life of 400,000 kilometers. This is the necessary baseline for entry into the heavy-duty sector. And fuel consumption for a standard 49-ton trailer rig is aimed at less than 11 kilograms per 100 kilometers.
What are the 2030 technical priorities to achieve that balance of efficiency and durability?
They must first master low-to-mid pressure H2 GDI technology, which allows for much more precise combustion control than older port injection methods. And crucially, given the high pressures and corrosive nature of hydrogen under certain conditions, they must develop specialized anti-hydrogen embrittlement materials for all components, piping, and seals.
A material science challenge.
A huge one. It requires a leap in material science to ensure components don't fracture or degrade prematurely.
Moving to 2035, the CVH2 strategy demands simultaneous leaps in performance and reliability.
It really does. The 2035 targets are a max TE of 50%, matching the ultimate PC goal, but demanding a massive increase in reliability. B10 life must hit 700,000 kilometers. Power density, the sheer amount of power generated per liter of engine displacement, must also increase significantly to 29 kBOL to ensure the new hydrogen engine fits within the physical space constraints of heavy trucks.
A 500,000-kilometer reliability jump in just 5 years, plus 50% efficiency. How is that even realized in the combustion system?
This is where they have to move beyond conventional GDI. They plan to explore highly differentiated combustion technologies, such as jet ignition.
Jet ignition.
Imagine a tiny pre-combustion chamber where a highly efficient spark starts the burn, and that flame front is then jetted into the main cylinder, accelerating the slow hydrogen burn dramatically. This is then combined with refined ultra-lean burn strategies using high compression ratios. The report specifies optimizing the whole air system turbochargers, intercoolers, to realize this ultra-lean, high-efficiency mode effectively.
And the pinnacle, The 2040 CVH2 goal.
The ultimate target for heavy haulage, max TE of 52% with B10 life reaching a staggering 1 million kilometers. Power density is pushed even further to 32 kilobit.
A million kilometers B10 life. That means the design and material science must be virtually flawless to guarantee that level of heavy-duty endurance across a mass-produced fleet.
Absolutely.
What's the final technological leap in combustion required for that?
By 2040, they must master high-pressure H2 GDI diffusion combustion and specialized techniques like dome swirl combustion technology. This refers to realizing a highly sophisticated multi-point high-pressure injection and mixing strategy under extreme operating conditions. Dome swirl specifically refers to shaping the top of the piston and the incoming charge air to create controlled vortexes, ensuring the hydrogen is mixed perfectly with the air just before ignition, maximizing efficiency and preventing knock. It requires total mastery of fluid dynamics within the cylinder.
Now we move to the most technically challenging and arguably most strategically important roadmap, commercial vehicle ammonia engines, or CVNH3. This is the high-risk, high-reward section driven by that domestic raw material advantage.
Indeed. The mission here is to validate ammonia's feasibility in the CV sector by systematically overcoming the combustion stability, toxicity, and emission challenges we discussed earlier. The core technical evolution here is defined as the progression from simple external mixing and pilot ignition to highly sophisticated, high-pressure internal direct injection.
Let's start with the aggressive 2030 goals for ammonia engines.
By 2030, max TE is targeted at 48%, which is exceptionally aggressive, even higher than the 2030 hydrogen passenger car target. B10 life must hit 400,000 kilometers. The NH3 consumption for that 49-ton trailer is targeted at less than 69 kilograms per 100 kilometers.
What foundational technologies must they master by 2030 to even make ammonia burn reliably enough to hit 48% efficiency? It seems like a huge jump.
The key is mastering initial stable combustion methods using gaseous NH3 port injection. But crucially, they must develop and deploy technology for in-situ catalytic cracking reforming.
A mini chemical plant on the truck.
That's a great way to think about it. It uses heat from the engine to crack a small amount of ammonia into hydrogen on board the vehicle. Why? Because that temporary H2 assist acts like a chemical accelerator, dramatically increasing the slow flame speed of the main ammonia fuel charge. This, along with implementing passive pre-combustion chambers, is necessary to solve that low flame speed problem and maintain stability.
So 2030 is about using hydrogen assistance to force the ammonia to burn stably and efficiently. What's the progression to 2035 where efficiency needs to hit 50%?
The 2035 goal pushes max TE to 50%, with B10 life hitting 700,000 kilometers and power density reaching 32 kilobarrel. The technical leap is massive. They must introduce liquid NH3 low-pressure direct injection, or LDI. This moves the fuel delivery directly inside the cylinder at much higher pressure, which significantly increases efficiency and control compared to port injection.
And what about that complex emission hurdle we discussed? The high NOx and the NH3 slip problem.
This is the phase where emission control becomes the central battleground. They will integrate the Miller cycle, a modification of the standard engine cycle that keeps intake valves open longer to reduce combustion temperature and improve efficiency, and upgrade the passive pre-chambers to active passive pre-chambers.
And after treatment.
Most importantly, the exhaust after-treatment system must introduce non-conventional emission after-treatment techniques. This implies moving beyond standard catalytic converters to complex, multi-stage chemical reactors that can handle the unique challenge of simultaneously reducing high levels of NOx and trapping or converting the toxic uncombusted NH3 slip.
So it could involve complex selective catalytic reduction, or SCR formulations.
Specifically tailored for ammonia exhaust.
This just confirms that the after-treatment challenge for ammonia is huge. It requires entirely new chemical engineering approaches on the vehicle itself. And finally, the 2040 vision for CVNH3.
By 2040, the ultimate goal is max TE of 52%, B10 life of 1 million kilometers, and power density of 35 kilobarrel. Consumption needs to drop to less than 64 kilograms per 100 kilometers. By this point, the ammonia engine must be a reliable, high-performance, and emissions-compliant alternative for long-haul and heavy freight, achieving that 15% market penetration goal.
What combustion and material science breakthroughs are required for that 2040 ammonia engine to be a mass-market reality?
The focus shifts to a liquid NH3 high-pressure GDI, the absolute cutting edge of injection technology, combined with stratified ultra-lean burn, or ULB.
Okay, stratified ULB. How does that work?
To make it work, you must perfectly control the spray. Imagine injecting fuel into the cylinder so that you create a small, localized zone that is rich enough to ignite easily, that's the stratified part, surrounded by a massive cushion of air. This prevents the slow ammonia flame from being extinguished and maximizes the fuel-to-air ratio. Beyond combustion, this 2040 vision is totally dependent on material science. They have to develop specialized materials like high-alloy steel and specific non-ferrous alloys, and advanced anti-corrosion coatings to resist the highly corrosive nature of liquid ammonia and guarantee that 1 million kilometer lifespan. Component fatigue, injector clogging, corrosion, it all has to be zeroed out.
If we step back and connect this to the bigger picture, the sheer magnitude of this roadmap is astonishing. It is a strategic mandate to transform every single aspect of engine design in just 15 years.
Absolutely. This is not incremental. It's a fundamental generational shift. The technological leap required across all four roadmaps, PCH2, CVH2, and CVNH3, is immense. We are talking about moving from basic, less controlled combustion methods like port injection or diesel pilot ignition toward highly sophisticated, high-pressure, intelligent direct injection systems
GDI for hydrogen, LDI for ammonia.
across every single vehicle segment. This is a demand for total mastery of thermodynamics, fluid dynamics, material science, and intelligent control algorithms all at the same time.
And what's the key takeaway for you, the learner, today? Why should we care about this highly technical deep dive into these targets?
I think the most crucial element is the strategic positioning. Zero-carbon engines are not defined in this extensive strategic report as some kind of technologically mandated fallback. They are positioned as a necessary complement to full electrification, specifically engineered to solve the hardest to decarbonize segments: heavy freight, long-haul transport, and high-load hybrid passenger systems.
So it's a calculated plan.
It is a calculated, exceptionally ambitious plan to systematically move the domestic industry from a fast follower in certain technologies to a global leader by 2040, all while securing energy supply and aggressively updating the entire industrial base in the process.
It is a remarkable vision, moving from concept to market leadership in less than 2 decades. The commitment level necessary to achieve that 15% penetration in heavy trucks by 2040 is staggering.
It is. However, as any good consultancy report must do, the source material identifies a massive strategic vulnerability that overshadows all this technical planning. And this is the final thought for you to explore.
What is it?
The success of this entire roadmap, the achievement of 50% or 52% thermal efficiency and those high market penetration rates, hinges entirely on the cost and the scale of the fuels. Specifically, the large-scale production, distribution, and affordability of green hydrogen and green ammonia.
Right. An engine with 52% thermal efficiency is completely useless if the fuel required to run it is prohibitively expensive or just unavailable at the truck stop when needed.
Exactly. So the final question is, will the fuel logistics, the development of the necessary pipeline and refueling infrastructure, and the massive production capacity for affordable green H2 and NH3 be able to keep pace with these hyper-aggressive engine efficiency and durability targets?
A huge puzzle.
That massive global logistical and cost puzzle remains the single biggest challenge to the success of this 2040 zero-carbon engine roadmap. The engine technology might be world-class, but if the green fuel supply is a failure, the entire strategy collapses. That's the challenge that ties engine technology back to global energy and trade policy.
A truly crucial systemic element to consider as we watch these technical roadmaps unfold. Thank you for guiding us through this incredibly detailed and ambitious technology blueprint.
My pleasure. It's a fascinating high-stakes game.
And thank you for joining us on this deep dive into the future of power. We'll see you next time.